So I'll talk about two recent results. The first one is joined with Zaher Hani from University of Michigan, and the second one is joined with Zaher Hani and Xiao, who is also from University of Michigan. And the first one concerns derivation of the wave kinetic equation in wave turbulence. The second one concerns derivation of the Boltzmann equation in kinetic theory. So these two questions, these two results, they are coming from different fields, but they are actually very much closely related, and they both kind of fall under the category of the so-called Hilbert 6 problem, and that is why I put this title here. And I'll start this presentation by briefly introducing what is known as the Hilbert 6 problem. Okay, so Hilbert 6 problem was one problem that Hilbert introduced in his speech in the 1900 ICM in Paris, and this falls under the title of the mathematical treatment of the axiom of physics. Of course, this title can be extremely broad, but actually later on, Hilbert wrote an expository article in which he specified actually two questions that fall under the category of this title. So the first one of them was the mathematical theory of probability, which we know that has been answered kind of in the 1930s, 40s. And then the second one is kind of the first main topic I'll be discussing in this talk, that is this justification of the derivation of the continuum of fluid mechanics, fluid equations from the microscopic particle system. So basically, you think that you have these fluids, which are continuum fluids, but actually microscopically they are made up by these particles like atoms and molecules and so on. And then these particles, they have their own kind of dynamics. They go in straight line, or they interact or kind of collide with each other. There is a complicated dynamics going on there. And then you want to kind of study the kind of collective behavior of these objects, and that should turn into the the fluid equations, the Euler and Navier-Stokes equations concerning for example, the evolution of the velocity fields. Okay, so this is, as we quote here, so it's the problem of developing mathematically the limiting process which lead from atomistic view to the laws of motion of continua. That was the original problem that Hilbert introduced, like kind of 120 years ago. Okay, so this problem, as of now, it has not been completely answered, but in the 20th century, there has been certainly a lot of huge amount of progress on this problem. And so I'm listing kind of one major approach or kind of strategy to solve to study of this problem. So let me say that this is not the only strategy, but this has been kind of, so far it has been the kind of the strategy that is the best understood. So basically we are understanding this passage from the microscopic particle system to the macroscopic fluid equations as a kind of a two-stage limiting process. So the first stage is a so-called kinetic limit. So we start with, okay, let me actually use this. The kinetic limit, where we start with the particle systems, and then we take the limit where the degree of freedom, number of objects, number of particles, goes to infinity. And then in the end, we derive this kinetic equation, which is called the Boltzmann equation. So we'll see what exactly that equation is, but basically it is an equation that is satisfied by the density functions of this particle system, and this density function describes like the distribution of the position and velocity of these particles, basically given a spatial range, given a spatial domain, given a velocity range, how many particles do you find in this particular range? Okay, so this is the first limit that goes from the particle system to the Boltzmann equation. And once we have the Boltzmann equation, we have these density functions. How do we turn it into the fluid equations? And this we do by the second step, which is the hydrodynamic limit. So basically, this limit is where we have a quantity which we'll introduce later, which is called representing the rate of collisions. So we are letting this quantity, this rate of collisions, to go to infinity. Equivalently, we're letting a so-called mean free path to go to 0. And then, moreover, we're assuming basically these density functions governed by the Boltzmann equation, they are kind of Gaussian in the velocity. Basically, that means for each position x, you're having a center velocity, and your velocity are kind of distributing according to Gaussian law around that center. And then we're going to turn that center velocity into the velocity of the fluid at a particular point x, and in this way we get the evolution of the velocity field. Okay, so in this way we turn the Boltzmann equation in this hydrodynamic limit where the mean free path goes to 0 to the fluid equations, to the Euler equation, which is either compressible or incompressible, viscous or non-viscous, depending on the regimes you are taking. Okay. So these are the two kind of stages of the limit. So in this talk, in the first half of this talk, I'll be focusing on the first stage, the kinetic limit. So second stage, there has been a lot of works, and things are more or less well understood. So for example, there is this work of Cavendish in the 80s, and the work of Damasi, Esposito, Leibowitz in the 80s, and more recently the work of Gauss and Saint-Raymond, and the work of Gallagher and Tristani, where they basically, in the kind of for our purpose of linking these two limits, so the second step is kind of well understood. So we'll kind of skip it for the rest of this talk. Okay, so now let's continue with the first step. We go from the particle systems to the Boltzmann equation. So let me first start by describing what is a particle system we're looking at. So see, we have n particles. So n is a degree of freedom that is supposed to go to infinity, and they lie in a fixed three-dimensional domain. So this domain you can think of as a whole space or kind of a boundary on the periodic. It doesn't matter for now. So n is going to infinity. And then these particles, they are going to have a certain size represented by this parameter epsilon, and epsilon is going to 0 in the limit. Okay, so they are kind of the small particles. And there are kind of some kind of interactions in between these particles. And there are, in reality, the interaction between particles can be complicated, but in this talk, we'll be focusing on perhaps the simplest case where the particles interact only by direct collisions and assume these collisions are elastic collisions. So in the end, when we get to the more general case where you have a general, let's say, potential representing the interaction between particles, but by any case, conceptually, this makes no difference. Okay, so we're assuming this elastic collision interaction, which leads to the so-called Hart-sphere system. So I didn't say the words here, but it's called the Hart-sphere system. Okay, so now we have these many particles which are round balls actually. I mean, we're simplifying the things as much as possible, and we have these interactions. So the formula for the collision we'll see on the next slide. And let me mention this scaling law between the parameters. So this n, which is goes to infinity, and this epsilon, which goes to 0. So this is a quantity n times epsilon square in 3 dimensions. So this is exactly the collision rate I was talking about previously. If you think of a fixed particle, then if you think of it as travels at time 1, then this n epsilon square is exactly the expected number of particles that it's going to collide with. So basically, if you fix any particle, this is like each particle is going to collide this many times in units, this many collisions in unit time. And conversely, there is a notion of so-called mean free path, which is kind of the time it takes, or kind of the length the particle travels before its first collision, which is essentially the kind of reciprocal of this quantity. Okay, so in this setup of deriving the Boltzmann equation, we're taking a so-called Boltzmann grad scaling, which was introduced first in 1940s, where we take this guy, this collision rate, or equivalent to the reciprocal of the mean free path, to be a unit, kind of a size 1, or kind of a constant, independent of n and epsilon. Of course, as I said, in the hydrodynamic limit, in the second step, you are going to take this to go to infinity, but for now, let's set this to be a constant. Okay, so we have this system, we have these interactions, and we have this relation, this scaling between the parameters. So just for you to see the law of collision, this is a pretty elementary thing which tells us that the omega is basically the vector connecting the centers of the particles, and then the velocity that are in the omega direction gets exchanged, as you see in the 1D collisions, and the velocity in the orthogonal direction, they don't change at all. So this is this elementary thing, and you can see this is a kind of time reversal and the volume preserving dynamical system, which will be in comparison with the Boltzmann equation we'll see later on, which will be time irreversible. Okay. As I described earlier, we're interested in the behavior and evolution of these density functions, which describe kind of statistical kind of information of the whole particle system. These are represented by these kind of S particle density functions. So here Fs, t is a time, so z is x and v. X is a position and v is a velocity, and z1, zs is the position and velocity of the s particles. And what does this density function mean? It just means that the probability density of finding the first particle at the position x1, velocity v1, the second particle at the position x2 and velocity v2, and the s particle at position xs and velocity vs. Okay, so you see these quantities, they completely determine the kind of the statistical information of the whole system. Okay, so the evolution of these quantities, if you start with the evolution of this dynamical system, you can, by the Lewis equation, you can write down the exact evolution of the exact dynamics of these densities. And moreover, at time 0, we assume that these densities are kind of factorized. Okay, they're factorized into these one particle density functions, which is the initial data, which depends on the position x and velocity v. So this factorization, we'll get back to this later, represents an important idea in physics that the behavior of different particles should be viewed as being independent, and this leads to this factorization. Okay, so now we have this system. We have these quantities we are looking at, and now the question is, how do we describe the time evolution of these density functions in the limit, in the kinetic limit where n goes to infinity? So this is basically the main kind of question we're asking in this first stage of limit, where we go from particle system to the Boltzmann equation. Okay. So in these slides, let me discuss the independence kind of more carefully. So the initial factorization, the fact that initial S particle density is factorized into one particle densities, represents the independence between the states of different particles. And this is actually goes back to the original idea of Boltzmann in the 19th century, that we are kind of viewing the states of different particles always kind of as independent, and namely that these independence at initial time, we expect it to be preserved in the limit, even with positive time evolutions. So if you think of it, this is a very kind of a subtle thing that that actually caused some controversy in the beginning of the kinetic theory. That if you have a collision between two particles, like here, after the collisions, you cannot say the behavior of two particles are independent. They will not be independent. However, the idea is that since collision is a low probability event, you can still say that with high probability, or kind of with the dominant in the dominant sense, these particles are still kind of independent for positive times. Oh, got the wrong direction. Okay, and this is called the propagation of chaos, okay, in the physics literature, and has been taken out by physicists kind of intuitively, but mathematically it's a huge challenge to actually justify this in in many different settings. Okay, so if we assume the propagational chaos, then we know that the multiple, the multiple point densities are factorized into one-point densities even at later times, and then we want to understand how this one-point density evolves, and this evolution is given by this famous Boltzmann equation, which is written down here. So let me explain just a little bit. So left-hand side is a transport. So if there was no collision at all, then the particles, they go linearly. If they go linearly, then the density function is going to evolve under the linear transport equation. Now the right-hand side is called the collision operator. It represents the effect of the collision that I just described. And what does this mean? This means the kind of conservation of momentum in the collision. This means conservation of kinetic energy in the collision. And these things means this is so-called the gain term in the Boltzmann equation, which represents a scenario where you have two particles collide to output some particle at this particular place x at velocity v. And this negative term called the loss term is representing the scenario where you have one particle at a position x and velocity v, it collides with someone else and kind of gets out of this velocity. Okay, so and this total effect gives exactly the evolution of this one-point density function. Okay, so this is the Boltzmann equation. So we see our goal is now clear. We want to justify this propagational chaos, propagational chaos here. I want to justify the evolution of the one particle densities by the Boltzmann equation. If we take this, if we justify the evolution of one particle densities by the Boltzmann equation, if we take the limit n goes to infinity. Okay, so now let us review a little bit the history. So of course everything started with the work of the idea of Boltzmann. And maybe earlier by Maxwell in the 19th century, which first wrote down this equation kind of under this assumption of propagational chaos. And then in the 1940s, 50s, there was a grad and later grad Stassignani who kind of first formulated this as a precise mathematical statement under this limit of the Boltzmann grad scaling. And then later on, they introduced this idea of BG hierarchy to this problem, which then led to this first major milestone of Lanford and also later on of King in 1975, who first reached the rigorous derivation of Boltzmann equation for sufficiently small time, t less than sufficient small constant. Okay, so this was the first milestone. It was kind of essentially the only milestone, kind of up to this time. And then after that, there has been a lot of subsequent results, which I'll not talk too carefully. So there's work of Illner and Poverenti, which obtain long-time extensions in the case where the collision rate is sufficiently small. In other words, when the mean free path is sufficiently large. And then this work of Gallagher, Sanrem, and Taxia, who kind of located a place where the original Lanford proof was kind of not fully rigorous, and they corrected, and they also obtained explicit convergence rates. And then after that, there has been works of Bodino, Gallagher, Sanrem, and Bodino, Gallagher, Sanrem, and Simonella, for the last 10 years, where they were able to derive various linear models and of perturbations around fluctuations around the Boltzmann equations. Again, satisfy kind of various kind of linear stochastic Boltzmann equations for short time and for the long time at the so-called Max-1 equilibrium. Okay, so let me mention that all these pre-results are kind of restricted to either the short time or restricted to other perturbative settings. For example, the Illner-Poverenti is restricted to the case of a sufficiently small collision rate. Yes?
What does short time mean?
Short time means your time is less than compared to is less than absolute constant compared to depending on the initial data, because you have your initial data, which is given by this guy. If you solve your Boltzmann equation with this initial data, you're going to have a short time existence result, and that short time is basically this time, the time where you have a convergent kind of a power series in time of this expansion.
Which must be depending on the
Depends on the initial data. Or you can think of it as the time where you have barely, on average, have barely started your first collision. Okay. On the other hand, the long time means that you're allowed to have like a 10 collision or even 100 collisions or even like on average like any finite number of collisions. Okay.
If you assume that the initial data is of size, if you assume that the initial data is of size 1, then you can show that you can take the time to be 0.1, some very explicit small constants.
Can we continue this? But
Okay.
let's continue, and we'll get back to this point later on. It's a very good question about the physics of the problem, which should be answered, and I think they have the answer for that.
Okay. However, in the context of Hilbert's sixth problem, where we need to match, remember it's a two-stage process, we need to match the hydrodynamic limits to the kinetic limits, and here we need to extend the derivation to non-perturbative settings, which means that we are considering arbitrarily long times and we're considering arbitrarily large collision rates, or kind of arbitrarily small mean free path. Okay, so there is actually there is scaling relation between the time and the size of mean free paths, which we'll not talk about. But in any case, the key thing is to go beyond this perturbative set. Okay, and here's the question: can we derive the Boltzmann equation for hard sphere dynamics for arbitrarily long times as long as the solution to the Boltzmann equation exists? I should say for arbitrarily large value of the collision rate and other things. But in case, so this will be answered positively in our main theorem. But let me say, before going to the theorem, let me first move to the next kind of almost completely parallel problem, where instead of the interaction collision between particles, we're describing the interaction between waves, and this exactly leads to the theory of wave turbulence. Okay, so this is the second thing. So you see, in the time of Hilbert's lecture, there was actually almost no study on quantum physics in 1900. But you see, in the 20th century, there has been a huge development of quantum physics, and then, of course, this naturally leads to the interest in this evolution of quantum objects, evolution of waves, and in particular the Schrödinger equation. Okay, and this leads to the question for the corresponding Hilbert sixth problem, namely the derivation of these kinetic equations. Again, they occur in the study of wave interactions, and this was the starting point of the theory of wave turbulence. So since everyone here is so familiar with wave turbulence, I'm not going to spend too much time describing the history, but the role of Boltzmann equation is replaced by that of wave kinetic equations, and theory started with the works in the 1920s, 30s concerning the wave kinetic equation and quantum Boltzmann equation. But it was really received this huge development after the milestone works of Hasselmann and Zakharov, where Hasselmann actually applied this to the theory of water wave, and Zakharov was the one who introduced this great idea of the Zakharov spectrum into the picture. And as of now, it is still a huge challenge mathematically to justify the emergence of these objects. Okay, and there is one more slide on application. I think many of you know application better than I do, but this picture is just taken from the front page of our very Simon's collaboration on wave turbulence, and this picture is taken from another paper which studied turbulence in plasma. Okay, so let's turn to the precise description. Again, I assume you are more or less familiar with this. I'll go go a little bit faster. So these particles, okay, they are replaced by the Fourier modes in the so-called homogeneous case, and in inhomogeneous case, they should be replaced by wave package, which depends both on the frequency and on the time. But in any case, we have these objects, now microscopic objects that are interacting. And then we're considering the so-called large box limit, where the box is size L, and if we're in 3 dimensions, and the number of modes is about L to 3, which is also degree of freedom. So I'm taking this L go to infinity, and then there is this strength of nonlinearity, strength of interaction, which is denoted by this value alpha, which will go to 0. Okay, so there is one difference, compared to the wave to the particle case. Let's talk about that in the next slide. So we have these objects, interacting objects, and the interaction is exactly given by any dispersive equation. But since we're considering the simplest possible case, the simplest possible case of nonlinear dispersive equation is perhaps this QE nonlinear Schrödinger equation, which we'll see in this form. Towards the end of the talk, I'm going to get to other kind of dispersive models, but this is the one we actually study in our second main result in this large periodic box. Okay, so we take alpha go to 0, L go to infinity, and again there is a scaling law between these two. So actually here there is a subtle difference between the homogeneous and inhomogeneous cases. In the so-called homogeneous case, actually there is some flexibility in the scaling law, and we can have this alpha times L to gamma equals 1 for gamma anything between 0 and 1. And in the inhomogeneous case, there is basically a scaling law where alpha times L to the 1/2, where gamma is 1/2. This scaling law exactly corresponds to the Boltzmann grad in the particle setting. Okay, so let's review the thing. We have these interacting objects corresponding to the particles, and we have this rule of interaction corresponding to the collisions. By the way, notice that here we have a cubic interaction instead of quadratic binary collision in the Boltzmann case, which will lead to one key difference in the behavior of the final equation you get. And okay, so we start with our initial data. So these represents the different object, the different Fourier modes, and then the initial states of different Fourier modes are again independent. So this is the kind of the initial profile, and these either k are kind of IID Gaussians, which represents independence. Okay. And finally, let me mention that the role of these one particle densities and s particle densities in the Boltzmann equation, in the Boltzmann case, is replaced by these 2-point correlations and 2 s-point correlations. Because in the case of Schrödinger, this u itself doesn't mean anything. U itself doesn't mean doesn't mean density. It's a mod u squared that means density, and so the kind of the 1-point density in the Boltzmann is corresponding to the 2-point correlations in the wave kinetic theory. Okay, so the kinetic time again, this corresponds to the mean free path. If you think the group velocity is 1, then the kinetic time is formally equal to mean free path, and you can show that this is of order alpha minus 2, and this alpha is a strength of nonlinearity, and this again means kind of the first time where a given mode interact with any other mode. So here, basically, if you take alpha equals L to minus 1/2, then the kinetic time is equal to L, which means the mean free path is the same size as the size of the box itself, which corresponds to the Boltzmann grad. Okay, and again, so you see the thing here is almost completely parallel up to this point. That as in the particle setting, we expect propagation of chaos. Again, these Fourier modes is supposed to be independent in the limits, even for later time. So in other words, if you take this rescale by kinetic time, then and for any different Fourier mode K1 Kr, these random variables, these Fourier modes are supposed to be independent. And again, if you have this independence, then the kind of the total statistical behavior of the whole system is going to be described by the statistical behavior of single modes, and these single modes is represented to some extent by the second moment. And by the way, let me mention that you also have formulas for the fourth, sixth, and higher moment, which was found in the work of Nazarenko, and this has also been rigorously justified by our results. Okay, but for now, let's just look at the second moment, which is kind of the main thing we have here, and they are expected to satisfy the so-called wave kinetic equation. You see this equation here. This is the same as the Boltzmann equation, except that Now this means the conservation of, still the conservation of momentum, conservation of the wave number. And this means conservation of energy or the resonance condition in terms of the Boltzmann equation. And then you see there are two differences. First of all, the left-hand side has no transport term, but this is simply because we are taking the homogeneous setting instead of inhomogeneous setting. We could have written down the inhomogeneous setting where we have a transport term on the left-hand side. The second thing is that the right-hand side, you have a cubic nonlinearity instead of quadratic, which comes from the fact that you have a cubic interaction compared to binary collisions in the case of Boltzmann. But otherwise, these two things are exactly the same. And so the nice thing is that what is written down as the quantum Boltzmann equation in 1920s, 30s, which has the name of quantum Boltzmann equation or Boltzmann-Nordheim equation or kind of a number of other names. And the nonlinearity in this equation is precisely a sum or difference of the quadratic nonlinearity in Boltzmann and the cubic nonlinearity in the wave equation. So see, these equations, they are really closely related. If you, for example, if you here replace, if you replace n plus n2 by kind of n plus n2 plus 1 or n plus n2 minus 1, you exactly get this quantum Boltzmann equation. Okay, and this is a kind of a remarks on the wave equation. So let me say that at this time the solution theory to both the Boltzmann equation and the wave equation has been there has been kind of a pretty little is known in the solution theory of both equations. In the Boltzmann equation, we know there is certain hydrodynamic limit, and in the wave equation, there is almost nothing known except there are known blow-up results due to Escobedo and Velasquez, and there are some of course there were Poisson's results, but there are some guesses on the existence of the KZ spectrum, although they are not justified mathematically. So yeah, but in any case, our goal is still just to derive these equations. It's not our consideration for now to study the behavior of this equation, which of course is a very important mathematical problem, but this will leave to the future. Okay, so maybe a list of previous mathematical results as in the Boltzmann case. So the first thing was starting point was of Sprung in 1977, and then who started the whole a program of studying the wave kinetic theory for a linear Schrödinger equation, but with the random potential. And then this was later completed in the work of Xiao and Semhofer and Yao, where they were able to derive the kinetic equation not only for the kinetic time scale, but also beyond the kinetic time scale, which is exclusively for the linear model. And then the Lucas Sprung, which was the first one to deal with nonlinear equations at equilibrium. And then, of course, the work of Buckmaster, Germain, Hani, and Chatat, which was really the work that started the study of the recent years, which was the first one concerning nonlinear off equilibrium results, but with a kind of a time scale much before the real kinetic time scale. And then later on, myself and Hani, and independently Kolo and Japan, was able to get to this kinetic scale to the kind of arbitrary 1 minus epsilon. And then later on, myself with Hani, we were the first to reach, in the concept Schrödinger equation, we were the first to reach the exact kinetic time scale for sufficiently small tau. You see, this result is kind of in spirit the same as the length of the result, where again you are deriving your kinetic equation for sufficiently small time, and the sufficient small time means the time that you have barely started your first collision or interaction. Okay, so let me also mention that there is also this work of Stefani and Tran who reached the same result, but for stochastic, for kind of a multidimensional KdV equation with stochastic forcing. Okay, so with this, we have briefly described the setup, background, and the history of both problems, both the derivation of Boltzmann in the kinetic theory and derivation of the wave kinetic equation, in wave turbulence. And you can see they are kind of mostly in parallel, although there are, of course, also considerable differences on technical level. Sorry. Okay, So now I think it's a good time that we introduce our main theorem. So the first one was joined with Hani from last year. Basically, I should say that in dimension 3 and higher, I forgot to put it here. Suppose, but let's read it. Suppose the solution to the n tau k to the wave kinetic equation, exists on any fixed time interval. So let's say you give any fixed time interval 0 to tau star, well, tau star can be arbitrarily large, and then you assume your solution exists on this time 0 to tau star. So note that here we are not in the perturbable regime because the tau star can be arbitrarily large and the initial data n can also be arbitrarily large. Then we have this precise description of the limit. The second model moment that we are looking at is equal to the solution to the wave kinetic equation plus an explicit error term, kind of uniforming in all the variable with a uniform convergence rate. And this, of course, this is the one 2-point correlation. But we have all supplementary results such as propagational chaos and all other things that all occur kind of on the full interval 0 tau star where you have the solution. So basically, that's you think of it as this. Like if you have any solution, well, even tau star is infinity. We'll see in the next slide. Even tau star is infinity, then we can get this not infinity, but to a value that diverges in the limit in case you have global existence. Okay, so this is pretty much as the best that you can hope for, because if you don't have, the solution doesn't exist at all, then there is no point in talking about this approximation, and of course your whole theory do need to be adjusted, and in the kind of range where we still expect the whole theory to be valid, this is the best result that we can possibly hope for. And more recently, earlier this year, we have this same long-time result for the Boltzmann equation, which completes basically the first limiting process in the Hilbert 6 problem. So we'll say how do we connect to the second stage in the last few slides. Okay, suppose the solution to the Boltzmann equation exists again on any given interval. Again, T star can be arbitrarily large. This solution can be arbitrarily large. Then we have this. So you see, this is something that wraps up the propagational chaos and the Boltzmann approximation. The any S particle density is the tensor product of the solution to the Boltzmann equation plus the remainder. The remainder has an explicit convergence rate taken in the L1 norm in space and velocity. Okay, for fixed time. Epsilon is the parameter that goes to 0. It's the size of the particle that goes to 0. Okay, so this is our two main results. The first one is joined with Hani, and second one is joined with Hani and Ma. Okay, so let me make a few remarks concerning these results. So first of all, I think I already said this. In the case where either of these equations, in either theorem, if the equation has global solutions, okay, then we can actually allow this range tau star to go to infinity to diverge with our parameter L. So see, like this T star, or kind of this tau star, is allowed to go to infinity in the case of global existence. And this is very important because in many cases, for example, in typical case in the hydrodynamic limit, you do have a global solution. For example, a perturbation of Maxwellian in the torus, and you do have global solutions. And in this case, we are able to get to this long time, which actually go to infinity in the limit. And second, this theorem 2 of Boltzmann, the Hart sphere result, is stated in the case of RD, but it can be extended to a periodic case with minor modifications, and we'll do this in the subsequent work. And finally, as I mentioned earlier, there are various other models. The Schrödinger equation is, you can look at an inhomogeneous setting. You can look at a Schrödinger equation with Hartree interaction. And in the case of particles, you can look at general kind of interaction potentials, the so-called short-range potentials. They are expected to be true with the same strategies, but there are various complications. For example, in the Hartree case, you need to deal with these phase corrections. In the potential short-range potential case, you need to do more complicated expansion and so on. So technically, they can be more involved, but I believe the general strategy of proof will be the same. Okay, so we have a few more minutes. So let's leave it to the end. So before I'm planning to discuss a little bit of proof in the very end, but before that, let's discuss the kind of the future direction that we expect to work on. We expect that will be within reach, kind of with our main results. So first one is the quantum Boltzmann equation. So this one is the one that I just described, the one with both quadratic and cubic nonlinearities. And there is actually a question of what kind of microscopic model you need to start with. There is a model of the n-body problem, and there's a model based on the weak space formulation. And there's a subtlety between these two, whether or not they are exactly equivalent and exactly what kind of equation you are getting. And here the main difficulty of the derivation comes from the kind of non-commutativity of the object, so that you don't have a number of notations such as L-infinity normal or pointwise bound to use. Second, which is kind of more closely linked to the general topic of this meeting, the kind of the cascade, the energy cascade, and the formation of the singularity in the form of condensates, the delta is 0. So can we justify the emergence of KZ spectrum? Of course, this is one of the biggest problem in wave turbulence. So recently there is a work of Koller, Dieter, and Germain on the KZ spectrum. They basically prove some kind of stability of these objects, but it's still open whether or not these objects can dynamically occur from, for example, wave-Kane equations with forcing, and even if we can justify for the wave-Kane equation, whether or not we can derive it from the Schrödinger equation is also another main question, because those kind of KZ spectrum, they're singular solutions that do not fall in the category of our theorem. And the same question for the formation of delta singularities. Can you justify actually the formation of delta singularities with strong solutions before that? And in that case, what exactly do you expect to happen for the Schrödinger equation? So this is maybe one of the main questions to be asked kind of in this direction of cubic Schrödinger equation. Of course, like the cubic Schrödinger equation is just a very simplest example of non-dispersive equation, and there are many other non-dispersive equations, and moreover, our theorem is for high dimensions and what happens in one dimension. There are very much subtleties associated with quasi-linearity, and there are very much subtleties associated with 1D turbulence, like, for example, the 2D water wave problem, the MNT equations, the FPUT model. They're all in one dimension, and we actually, in calculation, we found there are also kind of anomalies kind of in every one of them that happen in one dimension. And do we need to modify the theory actually in one dimension? And finally, what if the wave equation itself is locally ill-posed? So there's recent very nice work of Empas, Zoklu, and Ledger that prove that the wave equation associated with the MMT model actually ill-posed locally ill-posed in a pretty strong sense if you are above a certain range of parameters. In this case, what do you even mean by the wave turbulence theory? What do you even expect for the dispersive equation to behave? And these are all very much open questions that are to study. And finally, concerning the Boltzmann equation, there is this problem of how do we connect the kinetic limit and hydrodynamic limit. In what range can we justify the prediction of Hilbert-6 problem? So we expect that we can justify this in a certain range, certain scaling between the n and epsilon. But what happens about other ranges? For example, instead of Boltzmann graph, you can consider so-called n equals epsilon minus 3 in 3D, and these things we expect it to be much more difficult. And this also links to the derivation of Landau equation, which is a setting where you have many more collisions. You're having infinite many collisions in time one in the limit. And how do we deal with these infinite many collisions? And is there a kind of a central limit type result happening, which we believe there will be in order to get a kind of a nice description? But this is something that is that seems pretty hard as of now. Okay, so if we still have a few more minutes, so I'll just briefly describe the proof. So there are kind of the overall strategies. So basically, you see the overall idea is that we already have the short time result by Lanford in the Boltzmann case and by our previous works in the wave case. So how to extend this strategy from the short time to long time? So first step is to do so-called time layering, or divide this long time interval into a large number of small time intervals. So we set this increment tau to be sufficiently small, such that we have a nice local theory, essentially. And then the main difficulty we see is that at initial time we have exact independence, kind of independent or complete factorization. But at a later time, we'll no longer have this complete factorization. So we're going to replace this factorization by a particular formula called the cumulative expansion formula, which tells us, for example, in the Boltzmann case, it writes as this: the S particle density is the sum of this factorized part. So this is the factorized part, and this is the so-called cumulative part, which is not factorized. However, this thing is expected to be small, and they're going to have a particular kind of expansion formula in terms of the interaction diagrams. So this is the kind of the first main point. We justify such a huge expression of the objects in terms of these huge diagrams called interaction diagrams, and then we should try to prove that these things are kind of under control without estimate. Is that a question?
No, but you did not mean the cumulants are small.
The cumulants, they are small. They are small. They are small in the Boltzmann case, they are small in L1 norm. In the Wilkian case, they are small pointwise. They are small.
1 plus
small. No, they are small, because you see, if cumulants is 1, then H is the whole thing. No, the H is empty. Then you sorry.
Cumulants is the empty set is 1.
Yeah. So if cumulants, yeah.
But when H is not empty, it is.
Yeah.
So there's something there. Otherwise, everything is vanished.
Yeah, for to say, but okay. And then the second half of the theorem concerns the actual control of these interaction history diagrams. And then we'll need to say that so there is an analytical component, there is a combinatorial component. So basically, what happens is that these quantities, where these cumulants, they are written as huge kind of integral expressions associated with these diagrams, which we call molecules. Okay, and then the first step is going to analyze this integral. We provide the upper bound on the integral, provided we know some nice structure about the molecule. Okay, and this step is actually an easy step. It just concerns direct volume estimate in the case of Boltzmann, in the case of Haas sphere. But in the case of wave kinetic, as this actually requires very delicate calculations and very delicate number theory estimates in the case of wave turbulence. But in any case, this is the first step. And the second step is the combinatorial component, where we remember in the first step, we reduce the estimate of the whole thing to a combinatorial property. And the second step, we're going to prove this combinatorial property by devising a so-called cutting algorithm. And this cutting algorithm actually is turns out to be exactly the opposite. It's kind of easier in the it's kind of easier in the wave kinetic case, and in the Boltzmann case, it actually requires a delicate combination of different strategies to deal with the molecule. But in any case, this is the second stage where we kind of provide this algorithm to prove that the given interaction diagram does have the good properties, and then this leads to the conclusion of the proof. Okay, so I'll stop here.
Thank you.